So what is an impulse? So impulse, ideally, mathematically, to describe an impulse, you need to understand the so-called delta function. So somebody doesn't believe that's a function because the definition is really weird. So what this function does, so we assume there is a time-dependent function as shown here. So this function is very special when, join here, a time function that is a data t. So this function is all 0 when time is smaller than 0. And then this function is 0 when the time is all positive. This function has a value only when it is at time equal to 0. Oops. And then this value is infinite. So it's really weird. So you don't have one non-zero value at one point, and then it's infinite. But the other interesting thing is the integration of these functions with respect to time from minus infinite to positive infinite is 1. So even though the value is infinite, but then there is a, you can find it like the integration is actually finite. So that's why this function is special. And there is another way to define such a function. You can use infinite small assumptions. What you assume is, you assume there is a square in the 2D time domain. The area of this square is 1. And then the width of this square is 2 epsilon. And then the height of this square is going to be 1 divided by 2 epsilon. So your delta function is when your epsilon approaches 0. And then you eventually get your delta function. All right. So that's an ideal impulse in math. So this function is interesting because it only appears on paper. In practice, there's nothing close to this impulse function. Well, so when we talk about impulse, we have to mention a physical theorem. It's called impulse momentum theorem. So that's when you apply the force, and then this force lasts for a certain period of time. And then so that force times force multiply the time is going to generate a momentum. So basically that's going to change the velocity of your object. So let's look at these spring mass damper system here. So we already learned that the equation of motion is mc k times ft, right? So that's what we have learned in previous lectures. But in this case, your force excitation is very special. It's no longer harmonic. It's actually a impulse. All right. So it's not easy to solve these functions directly because your impulse is a discontinuous function and it has a value of infinite. So if you directly put the force term in these ODE, it's really hard to solve it. But what you can do is you can apply the impulse momentum theorem, and then because you already know that your impulse, that's your F naught, is going to create the initial velocity. So eventually, this ODE is equivalent to free vibration subject to a initial velocity. V naught. And then this initial velocity is related to the force, the impulse amplitude divided by the mass. We got this equation from the impulse momentum theorem. So in other words, when you have a system subject to impulse excitation, it's actually equivalent to a system subject to an initial velocity. So we're going to learn how it looks like. So that's why you can refer back to lecture 3 or lecture 4. So we have the free damped vibration of a first order system. So your response simply depends on initial velocity and initial position. So here we only discuss the under damped condition, but in the homework, I have a homework question ask you to solve for over damped system. So you can give it a shot. So for under damped system, if it's subject to free vibration, then you can remember that the response is something like this, right? So the amplitude is decaying exponentially, and then the oscillation frequency is omega d. We call this damped natural frequency. And then from these amplitude decaying, you can get the damping ratio. And then if you have omega d, then you can get an omega n. So that means from free damped vibration, you're able to derive all the system parameters. So, yep.
So in MATLAB, we would treat it just like a free, damped free vibration as well, correct?
Well, I actually post 2 MATLAB codes on Blackboard. You can actually solve them directly if you're using the ODE's, the D solver.
Okay, gotcha.
Function.
I was kind of curious because when we were bringing up the that delta function, and you said that the only time it has any value outside of 0 is at 0, and it's equal to being infinite, correct?
Yep.
Okay. So how does
in MATLAB, because if it's on paper or in a software, then you can create that ideal impulse. In MATLAB, that function is called delta function. You can search the help file to check what the delta is. But then the delta function, I think there is a bug in MATLAB. So this delta function, when your impulse is at 0, that's going to give you trouble. I'm gonna explain that using a example later. So for free vibration, so if we have an impulse that is f hat over delta t, according to the impulse momentum theorem, that gives us the initial velocity, right? The initial velocity is just f hat over m. But it will never give us initial position. So your initial position is 0. So you can plug this initial velocity and initial position back into the free damped condition. So what you have is your fxt will be, so if you look at here, your x naught is 0. So let me erase all the 0 terms. That's going to be 0. This is 0. And then if you look at the 5 term, the top is 0, right? So your xt will become v naught e minus zeta omega n t sine omega d plus, because that's invert tangent of 0, so your phase lag is also 0. So that's going to be your impulse response. And remember that your v naught is f hat over m. So that gives you the Yeah, oh, I forget one thing. There is another omega d in the denominator. That's from the omega n times 1 minus zeta squared. So this is your response. So for convenience, in this lecture, we defined a edge function. So the underlying part, we named it as edge t. That's the edge function. So you don't have to copy and paste these lengthy expressions each and every time. All right. So that's the impulse when your impulse is applied at time equal to 0. So there's another case when your impulse is not at time equal to 0. So in this case, if it's delta t minus tau, that means your delta function is delayed by a time period of tau. So that means if you plot the delta function here, delta t minus tau, so that means the infinite impulse is going to happen at time equals to tau. Make sense? So if it's directly delta t, then your function is at time equal to 0. But then if you put t minus tau as the input, then you manually delayed your impulse by tau. All right. So if it's delayed by tau, then your xt is just f hat multiply edge delayed by tau, right? Means I can give an example. We already know that your system is underdamped, and then impulse applied at t equal to 0. So then your response, as I said, is going to be the same as a free vibration. So it starts from 0, oscillates, and goes back to 0. So if we delayed our impulse by tau, that's your excitation is delta t. If your excitation is t minus tau, or delayed by tau seconds, then you're going to expect the same response. It's just that your response is also delayed by tau, right? So that's tau, and then your response will be something like this. So that's why when your excitation is an impulse delayed by tau seconds, so most of them are the same. You only need to delay your edge function by tau. So how it looks like, so that you just replace all the t by tau. So then you can get everything. Remember, in this case, this function only exists when time is greater than tau. When time is smaller or equal than tau, then your edge function should be 0 because no excitation beyond that time point. All right. So let's look at a few examples. So let's look at these multiple impulsive excitations. So we have an underdamped system. So the system is driven by the force. But then if you look at the force, it actually has two impulse functions applied. And then it's also subject to an initial condition. So because your system is linear, so as I said, you can divide your system into a few subsystems. So the first subsystem is always your homogeneous solution or homogeneous function or initial condition, right? In this case, the first solution, the solution of the first subsystem, because your system is initially at rest, so it shouldn't give you any response. And then if you look at the second system, that's your first impulse input. So this impulse is applied at time equal to t1. So remember that your response should be the force amplitude times your h function, and then your h function should be delayed by t1 as well. The same thing, you have your f2 theta t minus t2. So your x3t equals to f2 h minus, oops. Right? So you have your solutions for, you have the solutions for each subsystem. And because of linear, because your system is linear, you can use superposition. The total solution will be h1t plus h2t plus h3t. But then you have to pay attention. So these x2 only exist when time is greater or equal than t1. x3 exists when time is greater and equal to t2. Before that, your subsystem number 3 won't exist. So your response should be 0. So that's why you have to write your equation piecewisely. So actually, that's not the way to write an equation. So your equation will be x1t, that's when t greater than 0, smaller than t1, x1t plus x2t in this time window. And then all these three together. Oops. Yep. So that should be the final solution. So at the beginning, when time is smaller than t1, neither of these impulse excitations were applied. So you only have one subsystem in your response. So that is x1t. So when t is greater than t1, then your first impulse comes into play. So that's when you introduce your second subsystem into your solution. And then when time is greater than t2, then you have everything in your response. So you have to sum all the responses. So impulse is relatively easy because we're just using the conclusions from initial conditions. From free vibrations. So let's look at another example. So these will be slightly confusing, especially the initial condition, the initial velocity V0 here. So here we have a impulse force applied at time equal to 0. But then the special thing here is your system is not initially at rest. It's actually subject to an initial position and velocity. How should we solve this? So again, because it's a linear system, then we can decompose these two types of inputs. All right. So the first one, again, is homogeneous, ODE. The second one is due to force, excitation. You just need to find the solution for both cases. As your homogeneous solution, because it's free vibration subject to initial conditions. So then you have whatever you have here in this equation. So you have to copy and paste. It's A E minus zeta omega n t sine omega d t plus phi. So your phi and A, they are to be determined. They are determined by your initial condition. So the subsystem 2 is easy. So it's just F hat times H T directly, no time lag, no time delay. Then there are two options. Because we already know that your xt is x1t plus x2t, right? That's from superposition. But then let's recall that your A and 5 in your x1t, they're still to be determined. We haven't determined that yet. So there are two options. Option 1, you don't care when you solve for A and 5, you don't care about the x2. You just assume that your x1t equals to x0 equal to x0. So x1t time derivative equals to the initial velocity equal to v0. Or there is another option when your x1, instead of focus on x1 only, you want to focus on the x. So your x1 0 plus x2 0 equals to x0. Oops. Then my question is, which option is correct? To solve for A and 5. You need to find your A and 5, so you need two equations. And then these equations are from your initial condition, or your initial condition. And then you can either use option 1, in this case, you solve your initial condition only using the homogeneous solution. Or you use option 2, you include both, and then solve them, and then consider the combined effect in your initial condition equations. So any thoughts?
Is there a way we could see an example of this a little more? Like, I
believe so.
There is
I believe there is a homework, like your homework number 1. You're gonna have to deal with this because your initial condition is non-zero, and then you have an impulse input at time equal to 0. Then you would have to pick one of these options, how to solve for the A and 5. So then the question goes back to the 0 negative and 0 positive. I think I briefly mentioned that in previous lectures. So 0 negative and 0 positive, they're actually different, especially in this case when your system is discontinuous. So if you have your system, there's your time, there's your xt, the response is something like this. And then if you plot your velocity, xt dot, you can see the discontinuous. So when time equals 0, and then after that, you have a velocity. Oops. So that means at the location where you apply the impulse, you create a discontinuous, you create a discontinuity in your velocity. That's because of the impulse momentum theorem. Does that make sense?
Somewhat. It still seems like, so when case 2 is when we are dealing with like two impulse functions. Wait, sorry, no. I'm sorry, I'm just a little confused a bit still on the cases. I think I'll just have to see a little later on.
Let me draw it for you. Yes, this is a very confusing subject, so hopefully I can explain this right. So basically, let's record this. Let me draw two images side by side. Your t, your t. That's your displacement, that's your velocity, okay? Let's assume system is at rest. That means initial position is 0, initial velocity is 0. So as I said, your displacement will follow free damped system, right? And then before time equal to 0 is flat, right? No response. Make sense?
Yes, that makes sense.
Okay, so let's draw the velocity of this system. So when time is before 0 is flat, then the velocity is also 0, right? Because your velocity is a derivative of your xt. So when your time is greater than 0, then you check the slope. So it's initially a positive value, and then gradually decrease back to zero. So at this point, your velocity is 0, and then becomes negative velocity, right? And then returns back to 0. And then your velocity will be something like this. Make sense?
Yep.
But then there is a special location when time equal to 0. What happened to the velocity?
Well, technically, it's going to be going towards infinite initially, right?
Yeah. So mathematically, we call this point the discontinuous, right?
Correct.
So that's because you have an impulse. So in other words, an impulse excitation is going to create discontinuity to your system. So then I'm going to ask you a question. What's the velocity at time equals 0?
It would be infinite, correct? Or it would be undefined.
Yeah, it will be undefined. So there's no way you can tell because it's discontinuous. So at that point, it actually have two values. It can be 0, or it can be a, let's name these as, like, what should we do? Using W? Oh, that's omega. Let's use a point P. So it can be either 0 or be P. But then what we usually do is, instead of using time equal to 0, we assume time equal to 0 minus or negative 0. So what you're doing is, based on this definition, mathematically what it means is you start, the negative means you start from the negative infinite. So you look at this equation starting from the negative infinite, and then assume it approaches 0 from that direction. What's the value? So that means these values should be 0, right?
Correct,
And
because
then,
it's flat before 0, correct?
yep. And then you can also define 0 positive. In this case, you assume that you're starting from time equal to infinite, large, and then you trace back and approach 0. Once it hits 0, what's the value there? It's actually p, right?
Correct.
So in our case, when t is greater than time 0 positive, we have xt equals to x1t plus x2t, right? We know that when t is greater than t plus, then your impulse comes into play. So that's why your system response have both components in it. But then when t is mathematically, like mathematicians, they may not like these symbols, but I just created that. So if we look from the negative time region, then your response is just x1 t, right? Because we assume that impulse is applied between, make sense? Before time is smaller than 0 minus, no impulse is applied. Once time is greater than 0 positive, then impulse is already applied. So the impulse is actually applied between these two time points. And then these two time points are infinitely small. I mean, this time period, this time span is infinite small.
Right. It's just like that very minuscule moment that we apply the impulse, correct?
Yep. So that's the confusing part, because luckily we are mechanical engineer. So this velocity discontinuity is not going to happen in any mechanical system, because there's no way you can change a velocity. You can abruptly change your velocity, right? If you drive a car, you cannot jump from 0 meters per second to 10 meters per second in infinite small amount of time. So physically, that's not impossible. That's not possible for us. That's a very critical concept for electric engineers, because in electric systems, that happens a lot. So then we have to go back to the initial condition. So what's the meaning of your initial position and initial velocity? Actually is 0 negative. Even though most of the time we say, okay, initial position is x naught equal to x when t equals to 0, it gives you t x naught. But this 0 is actually 0 negative.
Right. So that's before the system receives the impulse, correct?
Yes, that's actually, this initial condition is actually before the impulse comes into play. So that's why if you look at option 1 and option 2, so you have to use option 1. Your option 2 is wrong because it considers impulse response.
Right. And then in this case, for option 1, it's right before the impulse, so it's more valid, or is valid.
Yep. So that's the only thing, especially when you solve homework 1. I think that's going to trouble you, especially if you want to use MATLAB to solve homework 1. Like for MATLAB, I mentioned the delta function. In MATLAB, that is delta t.
And then for MATLAB, if we're using MATLAB in this one, will there be solutions for this particular problem as well?
Yep.
Okay, cool.
I actually have MATLAB code for these homework 1, but it's really, really confusing. I think MATLAB did something weird for delta t. So when you have time delay, for example, then you're using delta t minus 4. So MATLAB delta function can handle oops. So that means MATLAB. So what are you doing here is you use a dsolve, right? You just put your ODE function inside of the dsolve. Then inside of the, when you define the ODE function, you just define whatever, and then equals to delta t plus delta t minus 4, actually minus, right? So that's how you define an ODE function. ODE function, similar to what you did previously for the free vibration. But then MATLAB is able to handle these input correctly, but it won't be able to handle your data T. I don't know what MATLAB did. It seems that, so you have to play in a trick. So if you have delta T in your excitation, you have to multiply it by 2. If you do want to use MATLAB LiveScript to solve this ODE and with delta function, you have to multiply 2 for your delta T.
And that shouldn't change it, right?
Well, like mathematically, there's no explanation for that. I think that's a coding issue. I think the issue comes because of the Heaviside function in MATLAB. So you remember the integration of delta t is 1, right?
Correct.
So actually there's another function corresponds to this integration. It's called the Heaviside function. You can search this in MATLAB. That's the name of the function. So what it does is, if it's Heaviside t, no time lag. So this function before that is all 0. And then after time equals 0 is all 1. So this function is actually discontinuous. So I think MATLAB did some trick at time equals 0. So in fact, there shouldn't be any value at time equals 0. But what MATLAB did is it assumes that equals to 0.5. I think that 0.5 is going to give you the error in delta t. Anyway, so that's a lot of coding stuff. So if you don't want to learn MATLAB coding for these, you can just forget about it. If you do want to use dsolver, like if you do want to use a dsolve function to solve these homework number 1, you're going to run into trouble. And the trouble is from these coefficient too. You have to manually add that in front of your delta t. All right.
But once we add the 2, it should be fine, right?
Well, I forgot. I think it should be fine. I think so.
Okay, gotcha.
Mm-hmm.
Hopefully it is.
Yeah, hopefully it is. I think it's going to be fine when your initial conditions are all 0. But then if you have non-zero initial conditions, it might give you trouble again. So just being, I think the simple answer is if you see a data function with no time delay, just trying to avoid MATLAB. That's going to give you trouble. All right, so that's impulse response. Overall, I think is straightforward. You just need to remember these edge function. Your impulse is just your impulse amplitude times the edge function. if you have a time delay, you just delay your edge function as well. If you have more than one impulse, you just lump them together using a piecewise linear function. Okay. So if you understand impulse response, then we can start working on the arbitrary input. So assume that you have a force like this. It's just arbitrary. All right. So what you can do is you can divide your time span by n segments. You just divide it by n segments, and then each segment is data t in width. Let's just focus on these square, these small elements. So at these points, we assume we can approximate these when n approaches infinite. We can use a rectangular box. Make sense? So if you cut your arbitrary force function into small slices, then for each slice, you can use a rectangular box to approximate these segments. Let's zoom out on these rectangular box. We know that these one, the width is data t, and then we know the center of these boxes at time equal to ti. So that's why the force value or the height is the force value at t equals to ti, right? And then remember that your impulse is force times data t. That's your f hat at time equal to ti. So which means, oops, response due to ith segment. So that means for within each segment, you can assume there is an impulse. So what's the response of this impulse? So you can write it as x t equals to ti. So it's just f hat times h, because the time is delayed by ti. So you have to also delayed your h function by ti. And then you can plug your f hat back in. It's just a function. Oops. Delta t times h t minus ti. So that's the solution from ith segment. As I mentioned before, we divide these arbitrary force into n total segments. So we can use the superposition. So that means your total response is going to be the summation from the first segment all the way to the last segment. Within each segment, your response is something like this. And then as data t approaches 0 or n approaches infinite, so that means if we cut small enough, if we cut very, very tiny slice, then your summation becomes integration. It's no longer from 1 to n, it's actually from 0 to t. And then your force function we're using a different variable. So that's going to be your response when the excitation is just arbitrary. So this function is called convolution integral.
Quick question. Sorry,
Yeah.
I'm not able to, so below where it says as delta t approaches 0, there's another arrow, and then below that is n approaches
Infinity. Sorry.
oh, infinity. Okay,
Yeah.
I see.
So that means you're cutting your arbitrary force into infinite number of slices. Then your summation becomes integration. So that's when you have the arbitrary force excitation. Then you can use these so-called convolution integral to calculate your XT. Right? So you can also, so eventually there are two forms. You can either add time delay in your edge function, or you can add time delay in your force function. They're equivalent. Right? So there's a very special case, which is called step input. Let's assume you have MCK, a first order system, is subject to a FT. Your FT is a step input. Your system is initially at rest. Okay. So in this case, let's assume your T naught is 0. So that's, we can shift the axis. So that's time equal to 0. You're applying a step. So we can simplify the discussion. That's 0. That's time smaller than 0. So how that respond? So what's the response of this? So we already know that your X edge is integration from 0 to T F tau H T minus tau D tau. All right. So from 0 to T, we know that your F tau is a constant, right? So that's why you just replace your F tau by constant force. And then what is your edge T minus tau? You just copy and paste from the previous, copy from slide number 3. Okay. It's 1 over m omega d e minus zeta omega n t minus tau psi omega d t minus tau d tau. And then you can calculate this integration, and then eventually you're gonna get the solution here. That's your final solution. So the challenging part is you have to solve this integration. It's really complicated. So there are a few ways you can do it. You can either go Google and search integral table. So that's actually one of those common integration relations you can find on Google. So the other options, you can always use MATLAB for this purpose. I'm going to show you how to use MATLAB.
So wait, the first way to solve it was just to Google what?
Let me see. You just Google the integral table. Integral table. I can put it in the chat using that keyword. What is the chat? Okay, here we go. Yep. You just search this keyword and then find the formats that is the same as this equation, and then you can copy and paste. So that's how I did it when I don't know anything about MATLAB. But since I know MATLAB, you don't have to remember this table at all. It's already built in the live script. All right. So what you can do is, if you look at here, you have your zeta, you have your omega n, tau, omega dt, and then if you want, you can put an m and f naught. You can define these symbolic variables. They are real numbers, so that's why you can put a real in the end. So then let's calculate the integration. What is your function? Your function is f naught divided by m divided by omega d times exponential of minus zeta omega n tau. Oops, is that correct? T minus tau. T minus tau. And then right. So then you get an equation, and then eventually you just need to use the int function. That's the integral function in MATLAB. You first put in your symbolic function, then the second input is with respect to which variable you want to do the integration. In our case, it's tau. And then that's a lower bound, upper bound, and then if you click run, that should give you the result. You see that?
Oh, that's kind of neat.
Yep.
Really
So
complicated.
if you,
so it's like, what are we looking at? That's just it integrating with respect to tau. What do we use that for? That's a time response, right?
yeah, that's your time response. So that gives you the time domain response when your system is driven by a step input. Let me see. Share screen. So this convolution integral, it works for any input. It even works for the harmonic excitation. So that's the general method when you have a forced vibration system. So if you have mx double dot cx dot plus kx equal to ft, your ft can be anything as long as you know the force value at each time point. In order to find the xt response, you just need to calculate these integration. Oops. Right? So that's general. That works for any kind of force input. So that's why it works for arbitrary inputs. So here I give you an example. So that input is a step function. So before time equal to 0 is 0, your f is 0. But then after t equal to 0, then is a non-zero value. So if your f tau is really, really complicated, then this integration would become crazy. All right. Let me see anything here. All right. I think let's put an end to today's lecture. So any questions related to impulse and step response?